All right. So today we are going to finish up chapter 6. And then lab today is worksheet 6, which on terms of worksheets is kind of a short one. So I'm kind of hoping that we can, well, it's also kind of what you guys have questions on, but I was thinking that we would probably finish it in about half of the lab time. And then the other half of the lab time can be any questions you have for those 3 chapters, so 4, 5, and 6, since the next time I see you will be the test. So let me get our slides up here. There we go. Okay. So Monday, we talked about the first 3 types of mechanism steps. We talked about, trying to remember them in order, nucleophilic attack, loss of a leaving group, proton transfer. We're on to the 4th one. And what I ended with on Monday was this part up here. So this is looking at carbocation stability. When there's more carbons attached to that positively charged carbon, it's going to make it more stable. Down here is showing us why. So this does play into this 4th type of mechanism, just so you know. The goal of this 4th mechanism type is to create a more stable carbocation. So we just have to talk about which carbocations are more stable before we can make them more stable. So the reason why a tertiary carbocation is more stable than a secondary, which is more stable than a primary, is because of something called hyperconjugation. It's right here. Here is our carbocation, this guy right here. And the one that's being shown is primary, mostly because it gets kind of cluttered if we show secondary or tertiary, but this is going to show what's happening. And those are the abbreviations: primary, secondary, tertiary, by the way. So this primary carbocation has 1 carbon attached to it. That's what makes it primary. And in this example, it's a methyl, but it could be any carbon group. Any carbon size doesn't matter. A carbocation has an empty p orbital. And so that's what this and this, those are the empty p orbital. The second picture is a representation of hyperconjugation. So the carbon that's on the right-hand side, that is our carbocation, our positively charged carbon with its empty p orbital. The carbon that's on the left is that methyl group. That's what's making it a primary carbocation. The orbitals that are shown right here, that's just the bond between that carbon and one of its hydrogens. So this is just the sp3 orbital for that carbon. Hyperconjugation happens when there's a side-to-side overlap between the carbocation's empty orbital and the neighboring carbon's hybridized orbitals or filled orbitals. So the electrons that are in that sp3 orbital start to overlap into that empty orbital. This is the same idea that we've talked about with resonance. And so when this happens, we are kind of spreading out that positive charge. The charge is getting shared between more than one atom. And anytime we can spread out the charge, that means that it's going to be more stable. So the example that's shown here is with a primary carbon. That primary or that methyl group that's attached, we're showing the overlap with just one of its hydrogens. But as that bond rotates, there's 2 more bonds there that can overlap with that empty orbital. So that means that every carbon that's attached can overlap 3 times because it has 3 more bonds. So if we have a secondary carbocation, that means it has 6 bonds that it can overlap with. And if we have tertiary, it has 9 bonds it can overlap with. So as we add on those carbons, we have an increase in what can overlap. And this is also shown with a methyl, so it's a CH bond, but this could just as easily be another carbon here that's bonded to other hydrogens. We often show it as primary with a methyl attached just because the more carbons we add is just going to make it busier and a little messier, but it's just the bond that matters. It doesn't matter what it's bonded to. And we will talk about hyperconjugation occasionally. It comes up in chapters. Mostly we're using it to talk about carbocation stability, but it will come up occasionally in some other chapters, and I'll give you a little 2-minute reminder of what it is. Okay, so we know which types of carbocations are more stable. We know why they're more stable. This takes us to our 4th mechanism type, which is called a rearrangement. In some mechanisms, a carbocation will form. So for example, if we have a leaving group and that leaving group leaves, I'm going to go up here, it can create a carbocation. Whoops, need the L of that chlorine. There we go. Once we have a carbocation in an intermediate, this 4th type of rearrangement can happen. And what happens is that a rearrangement can occur, which either means a hydrogen or a methyl group can move in order to create a more stable carbocation. So there's 2 ways that this can happen: a 1,2 hydride shift or a 1,2 methyl shift. So there's a couple rules that we have to follow. One of them is this can only occur from an adjacent carbon. So that means that the hydrogen or the methyl that is shifting over has to come from the carbon next door. That's also why it's called a 1,2 shift. So a lot of times when we have mechanisms or reaction names that include numbering, the numbers have nothing to do with how we would name the structure. It has to do with where the reaction is taking place. So when it's labeled as a 1,2 hydride shift, that means that the carbons that are involved are right next to each other, 1,2. The second rule here says that it's only going to occur if a more stable carbocation can form. So let's look at the examples on here. In the first one, we are starting with a secondary carbocation. And I know it's secondary. There's my carbon. It's bonded to 1, 2 carbons. That's all it is. We're just counting how many carbons it's bonded to. That makes it secondary. I'm going to erase my blue there just because it's kind of in the way. Whoops, sorry. This is called a 1,2 hydride shift. So we got to talk about that word hydride real quick. Ide comes up in a couple different naming things. You talk about it a lot in general chemistry. But one of the big things with nonmetals is that it's when it's negatively charged. That's chlorine. That's chloride. So a hydride means that it's a negatively charged hydrogen, which is weird. That's not a normal thing for us. But the reason why we're referring to it as a hydride is because of where that arrow is coming from. So notice that the arrow is starting at that bond. So that means that the hydrogen is moving over, but it's taking its electrons with it. So it's moving over as a negatively charged atom or negatively charged ion. So I bring this up not because the naming of it's important, but it's important to realize that One, the hydrogen is taking those electrons with it. And two, this isn't normal. Most of the time, the hydrogen gets pulled by somebody else's electrons. This is a rare occurrence where the hydrogen is, I was going to say the hydrogen steering the ship, which is, don't use ship analogies. I don't know where that came from, but where the hydrogen is kind of pushing the reaction forward. So the hydrogen's using those electrons to create a new bond. So in that arrow, we're going from the bond onto that carbocation. So we end up with a new bond between the carbon and the hydrogen, which means that carbon isn't positively charged anymore. The carbon where the hydrogen was is now the new carbocation, and notice that it is a tertiary carbocation. So this is fulfilling that second rule. It can only occur if it makes something more stable. So a methyl could become primary, which could become a secondary, could become tertiary. So we can only move up in that chain. The second type that can occur is a 1,2 methyl shift. So it's kind of the same idea, but instead of moving a hydrogen over, we're moving a methyl over with its electrons. So in this example, and really it's the same carbon structure, but again, we're starting with that secondary carbocation. Again, look at where that arrow is starting. It's starting at that bond. So that means that methyl is taking its electrons with it to create this new bond. And we create a tertiary carbocation instead. This mechanism step is not something that's going to happen by itself. This would not be a full reaction. But in a lot of mechanisms that we're going to learn, we have carbocation intermediates. And so this is one of those things that anytime we see a carbocation in a reaction, we have to have a little red flag that pops up that says, could this go through a rearrangement? Would a rearrangement make this more stable? And so it's something that we're going to have to consider every time we see a carbocation. So it's honestly kind of annoying because it's always there as an option or as a possibility. Questions about, well, let me see where our next slide is. Okay. Questions about the rearrangement, about our fourth one. Can you show the 3 carbons? Yes. So can we show the 3 carbons connected to make it tertiary? So here's our carbocation. It's bonded to 1, 2, 3 carbons. So we don't have to add a negative charge on the hydrogen. No, we don't. So we refer to it as a hydride, and I said it's a negative hydrogen because in that process, it's taking those electrons with it. So we can think of it as something that is negative, but it's never by itself long enough to technically have that charge. We just call it a hydride because it's taking those electrons instead of leaving them behind.
Can you show the secondary carbon? Is it just the 2 that are next to the methyl?
No. So here's our secondary carbon. It's bonded to 1, 2 carbons. Is that what you mean?
Yeah.
Okay.
So when determining whether it's primary, secondary, or tertiary, you just look at how many carbons are around the carbon cation, right?
Right.
Okay, thank you.
You're welcome. We are going to practice a bunch of these. So I'm not stopping here with looking at mechanism steps. But any other questions just on this one? One other question that sometimes comes up once you do start practicing these is whether you can do kind of like a chain reaction. And the answer is no. So we can only move a hydrogen or a methyl group from one carbon to the next door neighbor, and that's it. So you couldn't just keep going down a line in order to create something more stable. It doesn't work that way. So this is a one and done thing. Okay. Most mechanisms require more than one of these steps to happen. So the example that's on the top here is showing all 4 of these steps in order to create the final product. So we're starting with a proton transfer. Our alcohol on our carbon chain is bonding to a hydrogen. And then we have the loss of the leaving group. So right here it says minus water. That's telling us that the water is breaking off of our carbon chain. So it's essentially just kind of telling us that water is leaving. So we're not going to see it anymore in the reaction. And then we have a carbocation rearrangement. Specifically, this is a 1,2 methyl shift, because that's our methyl group right there moving over. So the carbocation that's right here, what kind of carbocation does it start off as?
Secondary.
That is secondary, good. And then our methyl group moves over. So what kind of carbocation do we have now?
Tertiary.
Perfect. And then in that last step, we're doing a nucleophilic attack. So we have a bromine, we have a carbocation. Is the bromine our nucleophile or our electrophile?
Nucleophile.
Good. Which makes our carbocation our electrophile. So remember, they're named after what they're attracted to. So a carbocation, a positively charged thing, is going to be attracted to electrons. So it's an electrophile. And a bromide, or something that's negatively charged, is going to be attracted to protons, or where are the protons at? They're in the nucleus. So it's a nucleophile. And so then we get our final product down there. Now, in that first little domino train up there at the top, we do see all 4 reactions, or all 4 mechanism patterns, but we're looking at them one at a time. In the example on the bottom here, we see 2 different mechanism patterns happening, but they're happening at the same time. So we have 2 arrows. We have one going from the alcohol onto that carbon. What kind of mechanism step do you think that is? It is a nucleophilic attack. And then the second thing that's happening right there, and what kind of step is that one?
Proton transfer.
So that one's not a proton transfer. There's no hydrogens there.
Loss of
leaving group.
Perfect. So when we have a group leave, and we use the word group just to kind of be generic, it can just be a single atom like this chlorine, or in the example above, right here, it could be an entire water molecule. So the word group is just kind of a generic term. But our chloride is leaving, and so what we end up with is that alcohol attached to our carbon group, and then our chloride leaving group off on the side. All right, let's practice some of these. So our first thing here, let me look at my, okay. We're just gonna label what each of these steps are as we look at them. So let's see, I think I'm gonna number them just to make them easier to talk about. Six, 7. Oh yeah, we don't need to number the last one because it's the product. Okay, so we have 7 steps. What's happening in step number 1? Which of our patterns? So
Would
our
it be proton transfer?
It is a proton transfer, good. So our oxygen is bonding to that hydrogen. HA, you probably recognize that from general chemistry, but that's just a generic way to write an acid. So we do the same thing in organic chemistry. We also sometimes write that, and it just means a generic base. We do both of those because sometimes it just doesn't really matter. It just means we need an acid or a base in there. And sometimes it means there's more than one thing in the solution that could be playing the role of the acid or the base. So what about step number 2? What's happening there? So go ahead.
Nucleophilic attack.
It is a nucleophilic attack. Good. So this would be an alcohol group here. The alcohol is doing a nucleophilic attack on that carbonyl carbon. And then that second arrow that's happening right here, this is really just part of resonance. So that doesn't get a mechanism label. It's just kind of part of the flow of the electrons that has to happen. What's going on in step number 3?
Is that one also a proton transfer?
It is. And what you will see, especially as we start to learn bigger mechanisms, honestly, not till next semester, but as we learn some bigger mechanisms, there's a lot of proton transfers. So as you're looking at practice problems at the end of the chapter, there's problems that look like this. Don't be alarmed if half of the steps are proton transfers. That's kind of just how it goes. So speaking of, what's number 4?
Proton transfer.
Proton transfer. What about number 5?
Nucleophilic attack?
Not quite. So I kind of see why you're saying that, but this one is
proton transfer again.
not a proton transfer.
So rearrangement.
You guys are so close, but so far. It's this arrow right here. What's happening with that arrow?
Loss of a leaving group.
That is the loss of a leaving group. So that water, and right here it's telling us that water is leaving. Because that water is taking those electrons with it, that is our leaving group. Let's see. What about number 6?
I had a question when you're done with number 6. You can finish and then I'll ask it.
Okay. So what's going on in number 6?
Nucleophilic attack.
Good. Okay. What's the question?
For number 3, how come it's a proton transfer? Like, would the nucleophilic attack have to be, the arrow have to be in like a certain carbon bond for it to be an attack?
So this is a good question, and this is something that doesn't get caught every semester. But a nucleophilic attack and a proton transfer are the exact same thing, except a proton transfer always involves a hydrogen, and a nucleophilic attack never involves a hydrogen. So what I mean by saying that they're the exact same thing is if we look at, okay, we'll just look at this guy. There's our nucleophile, and it's going to make a bond to our carbon, and then the other bond has to break. So we're forming a new bond to our carbon, and a previous bond has to break. Here's our base. So that's the conjugate base of the acid that we started with. It's forming a new bond to a hydrogen, and that old bond has to break. So when we're doing a nucleophilic attack, everything is happening at a carbon. And when we're doing a proton transfer, everything is happening at a hydrogen. But they're both still forming new bonds and breaking old bonds. It's just whether we're focusing on the carbon or we're focusing on a hydrogen. So they are super similar. It's just what atom is being looked at. That make sense?
Yeah, because I was just confused as to why number 3 would have not been the attack, because it's doing the same thing for 6, but then you said hydrogen and carbons.
Yep. So if you see a hydrogen involved, proton transfer. What about number 7?
Proton transfer.
Proton transfer. Questions? Okay.
Oh wait, yeah. Do we always look at the bigger arrow?
No, not necessarily. So the The only reason there's a difference in arrow sizes is because one arrow is like within a molecule, and then the other arrow is between two different molecules. So that's just because of like the difference in how close they were drawn to each other. But that's not necessarily going to help you decide.
Is the leaving group usually going to be water molecules?
No, water is common, but halogens are also very common. And then, of course, there's a bunch of other things, but those two, either halogens or water, will probably be the most common ones that you will see. Okay, can you explain what the OR is doing in number 5 with its arrow? Oh, so right here, this guy. When that water leaving group leaves, if we didn't have that second arrow, we would have a positively charged carbon in the middle. Oh, sorry. But our oxygen has lone pairs. It's going to be attracted to that positive charge. So when we add in that second arrow, what happens is that we create that double bond. So instead of having that positively charged carbon, why won't this erase? That's weird. Instead of having a positively charged carbon, which is not stable, we create that double bond between the oxygen and the carbon. Any other questions on this? Okay. So I think we've probably talked about most of the curved arrow rules, guidelines. But let's go over what's on our slide here, just as a reminder. Oh, let's see. So will we have to write products on the test that goes from wedge dashed to bond line? Jada, do you mean like this transformation on the bottom here? Okay. So the reason why that one's going from a wedge and a dash to something without any wedges or dashes is because the carbon in number 5 is tetrahedral. So we're showing it with the dashes and the wedges. And the carbon in number 6 is trigonal planar. So it gets shown as a flat structure. But neither one of these, let's see. Let me redraw number 5 for you. Number 5 could have just as easily have been drawn. Where did that weird line come from? I don't know why I can't erase today. That's annoying. So number 5 could have been drawn like this. We would have loss of a leaving group and then that double bond forming. Ignore that purple line at the top. I don't know why it's there. I can't erase it. So yeah, the dashes and wedges aren't a big part of this at all. Okay. All right, so some curved arrow stuff. The tail, so this is where the arrow starts. Tail, head. The tail of the arrow has to start at an electron source. So that either means it's going to start on a lone pair or it's going to start at a bond. Has to start where the electrons are. The head of the arrow, and this is where our arrow is going to end, has to land on a bond or, oh, well, sorry, I phrased my sentence wrong for the way this was written. It has to show the formation of a bond or the formation of a lone pair. To show the formation of a bond, this can actually be a couple things. So that means that it can end on an atom. This would be showing a single bond formation. It can also just end at a bond, and this would be showing the formation of, we'll put triple there too, a double or a triple bond. So the example that's on here, the first arrow, that one, we're starting at the lone pair of the oxygen and we're ending on that carbon. So we're creating a single bond between the oxygen and the carbon. And then the other arrow, it's starting at that bond, but it's landing on the chlorine. That's what's creating the lone pair on the chlorine. So in order to make a lone pair, we're going to end on an atom. Now, I do put these on here so that we can talk about them. Don't memorize this though, because notice that 2 of these end on atoms and they're making 2 different things. So where they start and where they end is going to tell you what type of thing is being created, whether we're breaking a bond, making a lone pair, making a double bond. So you have to recognize those patterns, not just memorize the rules. The last little bullet point there is a good reminder. Carbon, nitrogen, and oxygen can't have an expanded octet. These are the atoms we deal with the most. So it's really important to remember that as we are adding in electrons, adding in bonds, we aren't making a 5th bond. We're not giving it an extra lone pair that it can't take on. So if you need to draw in all of the lone pairs on all of the atoms so that you can see that, that's completely okay. Do what's going to make sense to you as you're working on these. All right, any questions about our guidelines? All right, then let's do some practice ones. Let me find my sheet here. So I do have a few blank slides. I have a few problems for us to do. So I had mentioned on Monday that you're going to see the mechanism problems in 3 ways on the test. One will be something like this, where you're telling me what type of pattern is happening at each step. So you're given the reactants, you're given the arrows, and you're given the products. Another type would be something like this. You're given the reactants, you're given the products. What we're going to do is fill in the arrows. So we're going to fill in the missing mechanism curved electron pushing arrows. So in step number 1, and actually let me turn on, so I turned on the screen annotation. Does anybody want to draw in the arrow for that first one? Double arrows, perfect. Yeah, that's exactly right. We're going from the bond onto the bromine. What type of step is that?
The loss of the leaving group.
Perfect.
Wait, do we need the double arrows?
No, that was just because 2 people answered it at once.
Oh, okay.
Good question, though. No. What about the second one? So we have an NH2 negative there. We have our carbocation. We have our product. What is our arrow going to look like for this one?
Nucleophilic attack.
It is a nucleophilic attack. Anyone want to draw in our arrow for it? I like that everyone decides at once to do it. So your arrows look good. All 3 of the arrows that ended up on there need a little bit of adjustment though. All 3 of them were starting on the hydrogen side of that molecule, and we want to have them start at the nitrogen. And if it helps, you can fill in the lone pairs on the nitrogen just so you can see them. And I'm going to go underneath. That part doesn't matter, but I'm going to start at that lone pair and go to the carbon. Now, the red and the blue arrows, where they're ending on the left or the right side of that carbon, that's completely okay. Mine ended underneath. That's completely okay. So all of them were ending correctly, but we need it to start at the nitrogen. So I'm going to, let's see, can I erase your guys' stuff? Oh, I can. Okay. So you don't have to draw in the lone pairs, but sometimes it can help just to give you a spot to start your arrow. But we do need it to start at the nitrogen and not the hydrogen. Questions on either one of those?
Will we ever have to draw the products and the arrows, or will we always be given one?
Eventually, yes, but not in this chapter.
Okay.
Anything else?
Is it going to be this straightforward on the test?
Yeah.
Okay, perfect. Thanks.
Oh yeah, I have to clear our drawings before I can switch slides. I always forget. Whoops. Oh, geez. There we go. All right, number 3. And number 4. What's going on in number 3?
We have a carbocation. So remove the pair of electrons.
We do have a carbocation. So if we look at the reactant and the product, what type of mechanism pattern do we think is happening?
Rearrangement?
Perfect. And do you think that this was a hydrogen rearrangement or a methyl rearrangement? What moved over?
Hydrogen.
Good. Whoops. Okay, so let me show you how to draw this one. I'm going to just do it in a different color just so we can see it stand out. I'm going to add in my hydrogen right there. And all we're doing is we're going from that bond onto the carbocation. We know it was a hydrogen shift and not a methyl shift because if we compare what we started with and what we ended with, the carbon structure hasn't changed. Now I'm going to draw in that green hydrogen just to show where it's at now. But that's where it's at. So it moved over from one carbon to the one next door. That's our 1,2 hydride shift. What kind of carbocation did we start with?
Secondary?
Secondary here.
Good. And what kind did we end with?
Tertiary?
Good. Questions on that one?
Can you do one with methyl?
Mm-hmm.
Just so I can kind of see, because I was a little confused on the hydrogen part.
So this is what it would look like without any arrows. So we know that it's a methyl shift because we can see that the carbon structure has changed. Our carbon over here had 3 methyl groups attached to it. And now there's only 2 methyl groups, but there's another methyl group on the side. So we can just see that the carbon skeleton has changed. So this is a 1,2 methyl shift. Here's how we're going to draw in the arrows for it. we're going to start at the bond and we're going to go to that carbocation. That's it. And so if we want to make the colors match, here is my methyl that shifted over. And so again, we went from that secondary carbocation to a tertiary carbocation. And that methyl group is the one that had to shift over to make that happen. Does that help?
Yeah, thank you.
You're welcome. Okay, let's go back to the one number 4 then. Let me turn on.
Professor, sorry. In this
That's
one,
okay.
you said that we ended up having a tertiary carbon.
A tertiary carbocation, uh-huh.
Okay.
You want me to point out why it's tertiary? Let me get.
Yes, please.
So here's our carbon that we're talking about. It's bonded to 1, 2, 3 other carbons.
Got it. So in the other one, we're starting on the second one, on the secondary carbocation?
Yes. So there's our carbon and it's bonded to 2 other carbons.
Oh, okay, I got it. Perfect.
Okay.
Thank you so much.
You're welcome. All right, what's happening in step number 4? Anyone want to draw in our mechanism arrow that's missing? Perfect. And what kind of step is that?
A proton transfer.
It is a proton transfer. So that the arrow starting location and ending location is completely perfect. If it helps you to see things, you can add in lone pairs. It is not a requirement. Sometimes it's nice to have that anchor point though for a starting location, just so that you know you've started it at electrons, but not required. All right, questions on this slide at all, on our rearrangement or our proton transfer? We have one more I'm going to put on the next slide. It's kind of a weird one. Saved the weird one for the end. Do we have to specify the type? So it kind of just depends on what the question's asking. So the question was, do we have to specify the type of rearrangement? Honestly, with this type of question on the test, I wouldn't have you do both. I would either have you fill in the arrows or have you tell me what type of oh, I'm sorry, I didn't even answer your question correctly. Do we have to specify what type of arrangement? No, so the questions on the test that will be like, what type of step is this? Those will actually be multiple choice questions, just to make it easy for you to circle an option. So it will just say rearrangement, or actually it'll probably say carbocation rearrangement, but it won't specify hydride or methyl. Okay. Sorry, Jada, I went off on a weird direction with that answer to start with. Okay. Oh, got to clear our annotation. Okay. There we go. So I'm going to do one more on the bottom down here. I'm going to turn on the annotation. This one's a little different though. So if you're hesitant, I understand why. That's okay. Anybody want to give this one a try? So when you
Is it
have
rearrangement?
it's not a rearrangement. Perfect. I like the teamwork there. So the red arrow, what kind of mechanism pattern is that red arrow?
It'll be loss of a leaving group.
So the blue arrow is, but that red arrow is a nucleophilic attack. So pi electrons, double bonds, can be a nucleophile. So our nucleophile, our pi electrons are bonding to that bromine. I'm going to erase this guy down here. And then the second arrow technically is the loss of a leaving group. because that second bromine is breaking that bond and taking the electrons with it. And so what we end up with is that first bromine is bonded to the carbon. So this arrow is a bond forming between the carbon and the bromine. And the other carbon ends up with a positive charge because it lost its electrons, it lost the bond. And then the other bromine takes those electrons with it. So we could fill in some lone pairs here. But our other bromine ends up as a bromide. It ends up as a negatively charged bromine on the side. Questions about that last one?
How was the
Arrow.
how was the pi bond broken, Professor?
How is it broken? Is that what you said?
Yes.
So the arrow is showing how it's breaking. Those electrons in that pi bond are being used to create a new bond. So, oh, yellow probably won't show up very good. Those electrons are these electrons. We're just repurposing them. We're reusing them for something else.
Perfect. So we don't need an extra step to indicate that we're breaking the pi bond, right?
No, this red arrow is doing that. So that red arrow is showing us that we're breaking the pi bond and using those electrons to form a new bond.
Excellent. Thank you, Professor.
You're welcome. Was there another question?
Yeah, you said pi bonds
Mhm.
can be nucleophilic or are nucleophilic.
I'm hesitating on how to answer that. Pi bonds are nucleophiles.
Okay.
Yeah. Any other questions?
I was just kind of confused on the placement of bromide on the final product.
Oh, the fact that it's just kind of like hanging out up here?
No, the other one.
Oh, okay.
Yeah. So when you move the pi bond, yeah, I'm just confused on how it goes there.
So let's see. I'm not quite sure how to answer your question, but I'm gonna do my best and we'll see if it answers it. So the pi bond is bonded right now to those two carbons. So when we use those electrons to make a bond to something else, the bromine has to be bonded to one of those two carbons. So we could have actually drawn it with the bromine on the left carbon, oops, and a carbocation on the right carbon, and that would be completely fine too. Technically, they're the exact same thing because it's symmetrical. But those electrons are going to stay tethered to one of those two carbons. They're not just going to take off on their own. So when that bromine attaches, it has to be bonded to one of those two vinylic carbons, the ones that have the pi electrons. Is that
Yeah, that answered my
Okay.
question. Thank you. Because I wasn't sure. I was thinking that it can also go the other way, like you said. It can go up instead of down.
yeah.
And it's just flipped, but I wasn't sure if that was a possibility.
It totally can. And so this is a symmetrical molecule. So drawing either way is actually the exact same thing. When we actually learn this reaction, and I think it's chapter 8, we'll talk about all the other sides of it, like which side the bromine is going to prefer. There's a whole other issue there. But for this one, we don't need to know that.
Okay, thank you.
You're welcome. Anything else? Okay. Oh. Oh, do I have more? I think I just gave myself an extra slide for spacing, but I think that was it. All right, so a little bit more on these carbocation rearrangements, partly because we have to be able to see if a rearrangement is possible. So the ones that we've looked at so far, I've told you this is going to rearrange, and we've looked at both types, hydrogen and methyl. But a lot of times, especially in later chapters, when we look at a structure, we have to decide, is this going to go through a carbocation rearrangement? What type? And then we can do that rearrangement And then normally that means we're moving on to the rest of the mechanism. So here's what we're going to be looking for to make that decision. Will a carbocation go through a rearrangement? It will only happen if the rearrangement is going to make it more stable. A hydrogen shift is going to happen before a methyl shift will happen. So if there's a carbocation and it's sandwiched between two carbons, and doing a hydrogen shift on one side would create tertiary, and a methyl shift on the other side would make it tertiary. So both sides could make it more stable. The hydrogen is going to happen first. Hydrogens are smaller, which means they're easier to shift over, and they're moving faster. So this is really a kinetics thing. The hydrogen can shift over before the methyl can. Now, we talked about the fact that methyls are the least stable, then primary, then secondary, and then tertiary. There is a group up here, though, that's more stable than tertiary carbocations. And this is when we have resonance. So if we have allylic or benzylic carbocations, so allylic would be next to a double bond, and benzylic is next to a benzene ring. Both of those have resonance, which is going to help stabilize that carbocation. So we know this. We learned about resonance. We drew these kinds of things. But because of that resonance, it puts those categories above the rest of them. All right, so we have 4 down here. And the question is, will they go through a carbocation rearrangement to become more stable? If so, what type of shift are they going to go through? And then we'll draw in what it will look like after that shift. So what about structure A? So let's start with, in structure A, what type of carbocation do we have?
Tertiary?
It's not tertiary. How many carbons is that guy bonded to?
Secondary.
There we go. Yeah, so we're not looking at how many bonds it has. We're looking at how many carbon bonds. So don't let that hydrogen throw you off. So is this going to go through a rearrangement?
Could you add a double bond to one of the carbons?
So we can't do any double bonds. The only thing we can do is either move a hydrogen over or move a methyl over, and with the goal of making a more stable carbocation.
So I don't think you can do anything in the first one.
So let's look at what our options are. So let's say we moved a hydrogen from this side. Trying to keep it looking the same. Nitrogen. What kind of carbocation would that be?
Secondary.
It's secondary. So really, that tells me that's not going to happen because it didn't become more stable. So I'm going to erase this purple arrow. What about on the other side? Let's shift over one of these methyl groups. And I'm only shifting over a methyl group because that carbon doesn't have any hydrogens to shift over. CH2, C, hydrogen, our new methyl we just moved over, carbon. That was supposed to be a methyl. Methyl, methyl. And then there's our carbocation on the end now. So what type of carbocation do we have now?
Tertiary.
Tertiary. So this tells me that yes, this is going to go through a carbocation rearrangement, specifically a 1,2 methyl shift. So I'm going to erase the purple because that's not happening. I don't want it to be on there and confuse us. Questions on the first one?
Yeah, can you explain how it's tertiary?
It's tertiary because that carbon is bonded to 1, 2, 3 other carbons. Does that make sense?
Yeah, so then that carbon would be the carbocation cation because it's giving away one of the methyls, right?
Yes. So whenever we do that shift, wherever the methyl or the hydrogen is coming from, that becomes the new carbocation because it just lost a bond.
Okay.
What about letter B down there on the bottom? What type of carbocation are we starting with?
Primary.
It is primary. Now, there's only one place that a shift can occur from because it's only bonded to one carbon. So do we think that this one is going to go through a rearrangement?
No.
Yes, because then that would, if it was shifted and the other carbon, if we use the other carbon, then it would be tertiary.
Good. So is it going to go through a hydride shift or a methyl shift?
Methyl shift.
It's going to go through a hydride shift because there is a hydrogen there. So if a hydrogen's available, that's going to move before a methyl would. So I'm going to draw in my hydrogen here. I'm going to grab a different color. We're going to do this. So we're starting at the bond and going right onto that carbon. And so what we end up with is that. And so we get a tertiary carbocation. And so this was a 1,2 hydride shift. Questions about that one? Okay. What about letter C? What type of carbocation do we have in that one?
Secondary.
It is secondary. So if we look at what's available to shift over, there is a hydrogen on this side and there's a hydrogen on this side. So because there's a hydrogen on each side, we know it's not going to go through a methyl shift. That's not an option because there's hydrogens available on both sides. Will it go through a hydride shift though? Oh, can you number the chain? So one of the questions was, can you number the chain? I don't see the 1, 2. We use the phrase 1, 2 to just say how close the atoms are that are participating. So 1, 2, 1, 2. It's not the same way we would number it in terms of naming something. It's really just describing how close the atoms are that are participating in the reaction. So what about letter C? Is it going to go through a hydride shift? Will one of those sides become more stable than it already is?
Could the hydrogen with the methyl going up be shifted to create a tertiary?
Yes, yes. So the arrow that's drawn on there looks perfect. I'm going to draw in our product. So it is tertiary. Now, if the hydrogen from the other side shifted over, it would also be tertiary. But that one's not going to happen. Why does this tertiary one form? Why does this hydride shift happen, but the other one doesn't?
Because the other one is attached to a benzene ring, or just like a ring in general.
So good guess, but it's not the ring that's preventing it.
It would create a double bond if it shifted over, so it wouldn't really do anything.
It's not going to create a double bond. So with all of these, we're just moving the hydrogen or the methyl over. We're not going to make double bonds with any of these.
Is it because that one has resonance?
Exactly. So this isn't just tertiary. This is tertiary benzylic. So this is as stable as it gets. Benzylic is more stable than allylic, because allylic, we can do that one arrow. We can show resonance one time, but benzylic, we can keep going around that ring. We have that domino effect. And so it has 4 resonance contributors. And tertiary has the most things attached to it. So this is like the most stable of the most stable. So because we can create something that's tertiary benzylic, it's happy, it's good to go. All right, what about letter D? What type of carbocation? Oh, let's see. This was a 1,2 hydride. Forgot the 2 in there. A 1,2 hydride shift. What about letter D? What type of carbocation are we starting with?
Secondary. Oh, sorry, tertiary.
It is tertiary. And specifically, it's tertiary allylic, because it's right next to that double bond. So remember, the carbons that are in the double bond are vinylic carbons, and then the carbons that are next to them are allylic carbons. Okay, is this going to go through a shift?
No.
I agree with you. So the options would be a hydride shift from here or a hydride shift from here. We're not going to participate in hydride shifts with sp2 or sp carbons. It has to be sp3. And so if it went out here, it would become primary. If it went down here, it would become secondary. And tertiary allylic is hard to beat. Really, the only thing that can beat it is our tertiary benzylic we had in the last one. So this one is a no carbocation rearrangement for that guy.
Can you show where it would be primary if you did do it?
Yeah, let's see. I'm going to erase the no just so I have some space here. So if we did this, we shifted that over. It would be right there. And that hydrogen that moved would be right there.
Thank you.
You're welcome.
And you said we can't shift if it's SP or SP2, right? It has to be SP3.
Correct. Let me erase the one that's not happening. Any other questions about our rearrangements? Okay. Oh, I forgot there was some annotation on that last one. It follows, it doesn't stay on the slide. All right. We have a couple slides to look at. Let me see what time we're at. Okay, we're good. We have a couple slides to look at whether or not these reaction steps are reversible. Now, I'm going to preface this by telling you that we are going to talk about this. And as we look at mechanisms in later chapters, this is something that will come up as well. So we will specifically talk about whether reactions are reversible when we look at individual mechanisms and individual reactions. Now, the reason why I'm giving you a little disclaimer here is because when we look at mechanisms, we are looking at them in a forward direction. Whether or not they can go, whether or not they're reversible or not, we are drawing the arrows on the reactants to show what the product will become. I say this because whether or not they're reversible or not isn't a big deal for us. It's not going to be a main topic in any of the reactions we talk about. So we do show reversible arrows, so equilibrium arrows, or just a regular reaction arrow to show that it's not reversible. But that will be indicated when we look at the actual reactions. So we are going to make some generalizations about our 4 reaction types. Nucleophilic attack. We already said that a nucleophilic attack and the loss of a leaving group are the opposites of each other. So this will be a reversible reaction if our nucleophile is also a good leaving group. So it can go backwards. So this is the nucleophilic attack. This is the loss of a leaving group. It's the same pieces, just in opposite orders. So this will be a reversible reaction if our nucleophile is also a good leaving group. Right now, you don't need to know what makes a leaving group a good leaving group. That's actually something we'll talk about in the next chapter. So this is something that will come up quite a bit next week and the week after. This is the same statement. Loss of a leaving group is going to be a reversible reaction if our leaving group is a good nucleophile. So it's the same thing that the last slide said, just in reverse order, because now we're focusing on the leaving group itself. So if the leaving group is also a good nucleophile, then it will be reversible. And again, you don't need to know what makes a nucleophile a good nucleophile or a bad nucleophile yet. That's a big topic in chapter 7. Proton transfer. Now this is more of an acid-base thing. So we did say that a proton transfer could also be labeled as an acid-base reaction. So this is actually like second semester Gen Chem stuff. But a proton transfer reaction is going to be reversible if, excuse me, my water. If the pKa difference is greater than 10. That shouldn't say greater. It's reversible. It should be say less than 10. Sorry. I don't know why that's. Let me reread that. Reversible if the pK. Yeah, that should totally say less than 10. Okay, so in the first example, we have water as our acid and 1, 2, 3, 4, butane as our conjugate acid. So we're looking at the pKa difference between the acid and the conjugate acid. Because that difference is greater than 10, then we will not have a reversible reaction. It will be irreversible because our conjugate acid isn't a strong enough acid to push the reaction in the opposite direction. In the second example, we still have water as our acid base, conjugate acid, conjugate base. But if we look at the pKa differences there, it's only a difference of 2.3. So they're very similar in their acid strength. So our water can act as an acid, but that tert-butanol can also act as an acid. This will come up occasionally as we look at specific reactions. But what this really means is most of the time we want to pick acids or bases that will prevent this from happening. So we have to make sure we're picking strong enough acids that will push the reaction forward and not allow it to go in reverse. So this comes into reagent selection as we look at specific reactions. All right, last one, I think. Last one. Last one is carbocation rearrangements. Not reversible. Well, usually not reversible. I always hesitate to say always and never because honestly, there's always exceptions, but usually not reversible. We know that a carbocation rearrangement happens to make something more stable. So if we go from a secondary to a tertiary carbocation, there's no reason for it to go back to that secondary carbocation. It's already more stable. So it's not going to go back to something that's less stable. Other considerations, Le Chatelier's principle. So if you remember back to, can't remember if that's even first semester or second semester, I haven't taught general chemistry in a while. Le Chatelier's principle tells us that if we shift an equilibrium It will rearrange itself to get back into equilibrium, essentially. And so this says, why is this reaction irreversible? So we have the loss of a leaving group. Technically, in this reaction, the carbon is the leaving group because of how the arrow is going. We're breaking the bond between that carbon and that nitrogen, and the electrons are going on to the carbon. That makes the carbon group the leaving group. So we make a carbanion, which we don't see very often, and we make this guy. What is that second thing there? It's kind of a weird way to ask that, but that nitrogen molecule. Why would this reaction be irreversible? So it kind of all go together.
Because the nitrogens would be stable, wouldn't they?
It is stable, so that means it's most likely not going to react with the carbanion. What state is that nitrogen going to be in? So that's an N2 molecule.
A gas?
It's a gas. So when we make a gas, it just bubbles away. And so because it's bubbling away, it can't go back and react with that carbanion because it's gone. Sometimes this is a good thing for us because if we create a gas and it's a side product, it's something we don't care about, and it just bubbles away, it gets rid of itself on its own. So sometimes,
Professor?
oh, go ahead.
Sorry to ask, if you pressurize these, would they be reversible?
So that's a good question. So if it's pressurized or if we keep it like in a closed container, then yes, we could force it to go in reverse. Any other questions about the reversibility of this? Not this one, but any of them. Okay, this is actually our last slide. We are done with chapter 6. So lab today is the worksheet for chapter 6. We still have like 10 minutes-ish left in class, I think. What time are we done? Yeah, 10 minutes left. So I'll hang out here, answer any questions you might have. But I will see you in lab in about 15 minutes. And we will work on chapter 6. And then I'll also just be there to answer any questions you have about the other 2 chapters. So if you want to talk about the chapter 4 or 5 worksheets or any lab reports, we can chat about that as well. But
Wait, can I talk about the chapter 5 worksheet right now?
Yeah, sure.
Okay. On page 3, I had some trouble with the second molecule as to figuring out if it's R or S.
Okay, I am pulling mine up right now so I can see it. On page 3, the second.
Yeah, it's the second one, top right.
Okay. Let me just share my screen because that will make it easier for us. Oh, let me do that again. I had my, okay. Let's make this a little bigger. There we go. Okay, so we have our stereo center right here, right?
Mm-hmm.
And we look at what's attached to it. Carbon, carbon, oxygen. So oxygen gets the highest priority. There's a hydrogen on a dashed line hiding back there. That's our 4th priority. So whether you draw that in or not doesn't really matter, but it is the 4th priority. So right now, carbon versus carbon is tied. This carbon is bonded to, that was a hydrogen, a hydrogen, a hydrogen, and an oxygen. This carbon is bonded to a hydrogen, and an oxygen. So they're still tied. But then we look at what those oxygens are bonded to. This oxygen is bonded to a carbon, and this oxygen is bonded to a hydrogen. Carbon has a higher atomic number. So this is our 2nd priority, and this is our 3rd priority. And so then when we look at the order, we do 1, 2, 3, and it's going counterclockwise around that carbocation, and that's how we get the S.
So another question I was going to ask was, does this start at the OH because of the wedge?
I'm not sure what you mean when you say does what start?
Like,
You mean
like the numbering, like how would we know which carbon to start at to be able to number?
we're ranking them based off of priorities, based off of their atomic number. And so when we look at what's directly attached to our center carbon, there's an oxygen, a carbon, and a carbon. Because the oxygen has a higher atomic number than the carbons, it gets to have priority number 1.
Okay. And then you got to look for the other parts to it on top of the carbon and the carbon, right?
Yeah,
Like
so
what
because they're tied, because they're both carbons, we move one atom at a time. So I always think of this as you have to look at it with blinders on. You only want to look at one atom at a time. And if it's tied, then you can move to the next thing. And you
Okay.
compare those. And in this case, they were still both tied because it was both an oxygen. So we move one more atom out, and that's where we broke the tie, because the oxygen on the top was bonded to a carbon and the oxygen on the bottom was bonded to a hydrogen. Carbon has a higher atomic number than a hydrogen, so it became the higher priority out of those two. Does that make sense?
And you said that oxygen, that's number 2, is bonded to that carbon, which would be that carbon right in the middle of it, right?
This
Right
carbon
there.
up
Okay.
here.
Okay, yeah, that's what I thought. Okay, perfect. Thank you.
You're welcome. Any other questions for me in our last couple minutes here?
I have a quick question.
Yeah.
On the 6.11 carbocation rearrangement examples that we did, can you explain D and how it's tertiary? Because I think I'm getting confused with the carbocation sign. Like I'm assuming that something is missing. But
So there is something missing. It's missing one of its bonds. That's why it's positively charged.
yes. So what would be like the 4 groups then?
Okay, 1 second. Let me pull up my slides again. Okay, so you said 6.11. So in these examples?
Yes, on D.
Okay. So letter D. Okay. So here's our carbocation, right? It is bonded to 1, 2, 3 carbons. That's what makes it tertiary. So it's a carbocation because it doesn't have 4 bonds. So it's missing its 4th bond, which, you know, we can kind of think of it as maybe it was a hydrogen. It doesn't really matter what it was, to be honest, but it has 3 bonds now.
Got it. So it's secondary?
It's tertiary. It's bonded to 3 carbons.
Okay, got it.
So this one up here is secondary because it's bonded to 2 carbons. So it does have a 3rd bond that's not shown, that's a hydrogen. So all of our carbocations are going to have 3 bonds. How many of those bonds are carbon bonds tells us whether it's primary, secondary, or tertiary. So this one over here is primary because it's bonded to 1 carbon. It has 2 other bonds, but those 2 other bonds are hydrogens.
Okay, got it. Thank you.
You're welcome.
I had a quick question, but it's on worksheet 4.
That's fine. Let me pull it up.
Well, I mean, I can ask you. So for the Hayward drawings, does it matter which way I'm? Like, how do I determine which way the atom is going, up or down? You know, is it the same way? Are you just turning the chair into the Hayward drawing? So if it was like axial, or if it was up in the chair structure, then it's up in the Hayward drawing?
Yeah, pretty much. As long as you don't like flip it upside down or something weird.
Okay, and then so like that goes for like if it's up in equatorial position, then it's just up is up and down is down.
Yeah. So like if we look at like this one right here, let's do it this way. So if we're looking at this one up here, the alcohol group is up and axial. This isopropyl group is up and equatorial. In our Hayworth, they're both pointing up.
Okay, so it's pretty black and white.
Yeah. And I say you don't want to flip it or anything. What I mean by that is you're taking that chair, our little lightning bolt, and you're kind of you're kind of just flattening it.
Okay.
So like these two carbons right here are these two carbons right here.
Okay.
So I put that little black dot to kind of like indicate where to kind of like follow that carbon around the ring from all three versions.
If you drew it like shifted, like for example, if my OH was where the isopropyl is and the isopropyl is where the black dot is, and then like that, would that be okay? Because if I count it differently?
That would be okay. Yeah, that would be okay.
As long
If
as-
your isopropyl and your alcohol were flipped though, so we had the left thing on the right and the right thing on the left, that's going to mess it up.
Okay.
But yeah, if you just kind of like shifted everything one going around the ring, either clockwise or counterclockwise, that's not going to be a problem at all.
Okay, and then if it was like an ethyl attached, do I need to draw out the ethyl? Like if you go scroll down?
No, let me see. I got to turn off annotation before I can scroll.
Oh, sorry.
No, it's okay. I just always forget. Like here? Oh, yeah. So in this one, it's drawn out as an ethyl, but we could just draw a line and put ET. That works too.
Okay, perfect.
So same thing like this one. At the top one, I put IPR for isopropyl. That looks horrible.
Okay.
So we could put IPR for isopropyl, or we could draw it out. Both things work.
Okay, thank you.
Sometimes I definitely tend to do the abbreviations and when we're doing things like this, especially like something like a tert-butyl, just because it takes up a lot less space.
Okay, and I know how you taught me you counted where the black dot for the chairs 1, 2, and then going around.
Uh-huh.
So for the Hayworth one, you count the far right one as 1, right? And you're just going in the same order?
Yeah, that's how I do it. Yep.
Okay, thank you.
You're welcome. Checking the time. Oh, we are just about at time. I was just wondering if you'd be able to share your exam. Oh, Emma, I definitely will. I haven't finished writing it yet. It's kind of written out, but it's on paper. I always write it by hand first because of all the structures. So once I get it typed out, it won't be till Thursday though. So, okay.
Okay. No, that's okay.
I was gonna say, I don't know how much that'll help you. I can look and see. I'm sure I have an old one though. I will look to see if I have an old one today that would be like similar enough that it would be beneficial.
That's okay. I'll be doing the review like Friday, Saturday. I'm probably going to split it into 2 instead of session. But yeah, I just wanted to see that way, like I can kind of reference like, yes, I tend to get a lot of questions like, oh, will this little thing be on the exam? Will that little thing be on the exam?
Of course.
Tell them a yes or a no or a maybe.
Yeah, definitely. So yeah, I'll send you the actual one, but I'll look and see if I have an old one that works.
Sounds good. Thank you so much.
You're welcome.
Bye-bye.
Bye.